Today we are talking about multivariate methods. So let's first talk about multivariate data. So in parametric methods, as we saw last week, we were estimating from a single variable x. But in general, we want to process a set of variables. We don't have just one instance, one variable. We have many of them that are usually put into a vector. So here we see our training set x with our label r. The xr vector is made of x1 t, x2 t, up to x dt. So we are working in d dimensions, and that is put in a vector of 1 by d. That is representing a single instance, a single sample. Many names can be used for variables. We could call them inputs, features, attributes. These are different names for the same thing, basically. It is more coming from the domain. In some domains, like pattern recognition, we are talking more about features, while in some others, we are talking more about attributes or inputs. And for a data, we could call this a sample data. It is also named an observation, an example, or an instance. These are all different names to qualify the data itself. So we can put all the dataset variables, measurements into a matrix. So this big matrix X is made of, is D by N. So we have D variables and N samples overall, N instances. The mean vector mu is defined as the mean of each column. So we are computing this as for variable 1 over all data instances from our data set. We are getting the mean for that variable as mu1 and then mu2 up to mu d. And packing all these means per variable, we get the mean vector, the mu, old mu, which is getting all these as the mean vector. And the variance, we can get also the variance of a variable xi, which is noted sigma I square. So this sigma I square is basically the usual variance we are computing, we are using in statistics. And we have also the covariance of two variables. So now, being in multiple dimensions, we can compute the covariance, that is how one variable vary according to another one. So we noted as sigma ij, the covariance of variable xi and xj. And this covariance is defined as this equation, which is kind of standard. So we are having here the expectation. So we are getting the expectation of xi variable xi minus its mean value times xj minus the mean of variable j. And this can be simplified as this one. So the expectation of xi times xj minus the product of the mean values for each of these variables. So we also have a covariance, which is noted as big sigma. So this covariance matrix is basically getting all variance over all combination of variables. So it is a squared D by D matrix, and it is also symmetrical, such as sigma 1, 2 is equal to sigma ij is equal to sigma ji. So here we see that sigma 1, 2 is corresponding to, is the same in fact on both sides of the diagonal. And we have on the diagonal the variance itself. So it's sigma I squared. This corresponds to the variance of the variable. So for computing it, it's basically the same that with the single variance that we have here, except that we are able to use a nice compact vectorial form. So we are using the big matrix X with all the values minus the vector mu. Time itself transpose, so x minus mu times x minus mu transpose, and we get the expectation over that. So that is simplified as these things minus the product of the mean vector with itself transpose. So this gives us the covariance matrix. And so if we look at a set of samples, we have here a set of samples, which are the white dots. We can see that these samples are centered around a mu value, which is really the center of the scatter of cloud of points. And then we have also a view, which is kind of a top view from a Gaussian 2D Gaussian distribution. So we can see the lighter yellow region, which is the IS. So this Gaussian distribution is kind of coming out from the screen. There is some kind of horizontal aspects, which is seen over all the different colors that give us some different elevation over that Gaussian distribution. That means that over the mean vector, which are the IS. So this is the most likeliest area of the distribution where we will get more points. The density of points is higher versus when we are into other places with darker shades. It is, I would say, less likely to have values there. The likelihood is lower. Now we will go into expanding what we saw last week in terms of estimating means and variance, for example, but dealing with the multivariate case. So here we have the estimation of the mean, which is defined basically as this thing. So it's basically into vectorial notation, the estimation of the mean vector, which is noted m here, m both, as it is a vector. We are summing all individual vectors for all samples, x1, x2, up to xn, and we divide this by n. So this is a relatively straightforward way to compute the mean. So it is the mean, the estimation of the mean vector. We can also state this differently by defining each component of the m vector as mi, and mi is corresponding to the sum of the xit over from 1 to n divided by n. So this gives us the same thing. Now we can also define big S as the estimator of the covariance matrix here. So we have the same kind of thing. So we have here S, for example, S1 square, which is the variance of variable 1, and so on the diagonal. So these are estimator of the variance. This is different. We are dealing with estimators, which are built from the data sets. So this is not exactly the same thing than the covariance matrix, which is the real thing about the distribution. And then likewise, it is a symmetric matrix, and the values are all over the diagonals are equivalent, like here. We have S12, which is also S12 there. And as for estimating these values, we have here the formula for estimating the variance over the diagonal. So this thing here is basically computing the sum of xit. So we are computing the value minus its mean for variable I, all this square divided by n after summing all these values. And as for the covariance estimations, it is also the sum over all instances. So it's basically xit minus mi times xjt minus mj. So we are making the sum by looking at the variables ij, and we are computing this over all data instances and dividing by n. And I may ask you to develop these equations, but it would not be fair in the sense that developing the equation for the covariance matrix estimator is complex. It requires the application of the spectral theorem. So this is beyond the course. You can simply trust this result, but if you want to know more, it is really well-known results, and you could find any information on how to derive this. But we are not looking further. We cannot apply maximum likelihood as is, because we are facing some situations where we need to use more advanced way to obtain these results in terms of the developments. There is also the notion of correlation between variables. So we can see here we have a correlation, which is noted rho ij. So this correlation is basically the covariance over variable I and j, but normalized according to the product of sigma I, sigma j. So this allows to look at the ratio between the covariance divided by the standard deviation of the two variables independently. The nice thing about this is that it is a way to standardize the measure. So the correlation is between -1 and 1. It's really limiting this because the product of sigma I, sigma j is always equal or larger than the sigma ij absolute value. So if we are looking at two independent variables, so where xi and xj has no relation, we will obtain a zero correlation. So basically here the covariance will be 0. So the correlation will also be 0. The inverse is, however, not true. So if we have a correlation of 0, that doesn't necessarily mean that these variables are independent. So if they are independent, the correlation is 0. But if the correlation is 0, it doesn't mean that the variables are independent. There might be some complex non-linear relation between these variables. And as such, we want to estimate correlation. So estimation of correlation is based on the estimation of covariance. So it's basically the same formula, but replacing the real values with the estimations. And we call the matrix big R as the matrix correlation matrix. So it's correlation matrix estimator, which contains the Rij. If we look at some distribution, at some set of points, data sets, we can see here on the top different normal Gaussian distributions with their associated correlation values. So if we have like a correlation of 1, it's pretty much a kind of 45 degrees angle, 10 lines of points. And as the value goes closer to 0, we can see something that looks like more kind of a well-spread point. So we can see that the sign here is somehow influencing the slope of corresponding to the biggest line across the samples. As we are getting close to 1, it means that the values are really well organized around that line. So, however, when we see a line, except for the first case here, which is kind of a little degenerated, we can see that in all other cases, when we get some kind of really direct relation where it seems to be a really direct function between the x and the y, we always have a correlation equal to either 1 or -1. When there are some spreading, the correlation is different from that. We can see on the lowest row cases where the correlation is nil. So we have a 0 correlation, but this is clearly not independent variables. We have different patterns, but it boils down to a 0 correlation measurement. So when we say 0 correlation doesn't mean independence, these are good examples. These 2D distribution over variable 1 and 2, there is clearly no independence. They are dependent, so these two variables are related, but not in a linear way, and in such a way that the correlation is 0.